As the Hulk says, you wouldn't like me when I'm angry. All right, residual magnetism. Magnetism left in the part after the magnetizing force is removed. All right, this is kind of an important point. This is stuff that I'm really going to need you to remember when we start working on non-destructive testing. I'm going to refer you back to this and say we've covered this. So, yeah, I know, you got to remember stuff, and that really stinks. So soft iron is easily magnetized. Easily magnetized, but once you remove the magnetism, it goes away. So soft iron is easily magnetized. Where am I at? But it has low residual magnetism. And we would call that low retentivity. Low retentivity. Strong steel, or strong iron, if I want to keep it the same way, strong steel and iron, same thing, such as carbon steel, is much more difficult to magnetize, much more difficult to magnetize, but has high residual magnetism, has high residual magnetism. And what's that word? High retentivity. Residual magnetism, also called retentivity. Then we have something called permeability. Permeability. It's the ability of a metal. I wrote ability of a metal to become magnetized. No way that's true. Permeability is the ability of a metal to become magnetized. So something can have high permeability, which means that it's easily magnetized, but how does that play into retentivity? That's a whole other thing. So I could easily magnetize something. So let's do this. So soft iron had high or low retentivity? Low retentivity. So soft iron has high permeability. Has pipe permeability. But it had what?
Low retentivity.
Low retentivity. Retentivity. So in other words, I can easily magnetize something that is soft iron, but the minute I remove the magnetizing force, what happens to it? Goes away. So if I want to talk about this in terms of non-destructive testing, which may or may not make much sense to you, I don't need a lot of amperage to magnetize something that is soft iron, and I can easily work with it within the machine on lower amp settings, but the minute I remove the current, I've lost the magnetism of it, or very little is left. And we can turn that around and say the opposite. So carbon steel then has high or low retentivity. Okay, so carbon steel has high. Well, we'll keep it in the same form.
Low
So
permeability.
carbon steel has high or low permeability?
Low.
Low permeability. Means it doesn't like to be magnetized. It's hard to get it that way, but once you get it that way, it stays. So high retentivity. And last but not least is reluctance. The opposition, that is the opposition of a material to magnetic lines of flux. So what does this mean? Where am I going with it? Anybody? Because I don't know.
Would it go hand in hand with the permeability?
Of course it does, to a sense. But why am I talking about this now? Because really this is a whole lot of stuff we need to know when we start a non-destructive testing. But we're working with a magneto, which its core piece is what? A rotating magnet. So we need to know a couple of things about this little magneto box. Why? Because every single aircraft out there that doesn't have a turbine engine on it's probably got two of these on it. And they're ubiquitous. They're everywhere. You have to know them. You're constantly dealing with them. So if you're in general aviation, you got to know it. If you don't want to do general aviation and you just want to get through here and go work for the airlines, guess what you're going to have to do when you go to your mechanic examiner? You're going to be working on one of these. So at one point or another, you're going to be working on them. I think as a mechanic examiner, every single test I had revolved around doing something with that. Checking the internal timing, checking to make sure it was installed on an engine, the theory of operation. So, but as far as the magnetism goes, what we're going to do is we're going to circle back around. We're going to talk about ignition now. But when we come back around to it, we're going to talk about why it's made the way it is. So it's got, of its core, it's got a magnet. Do I want that magnet to be soft steel or hard steel?
Hard steel, so it retains.
Hard steel, so it retains its magnetism. Okay, so it rotates in something called pole shoes. Do I want those pole shoes to be strong steel or soft steel?
Soft steel.
Why soft?
So it releases.
You don't want it to stay magnetized, because if it stayed magnetized, when the magnet comes back around, it has to demagnetize it and magnetize it the other way. You don't want that. You want, as the lines of flux go one way and the other, and the magnetism forms one way, the minute the magnet goes the other way, you want it to forget about its magnetism and just easily erase. So you want all of that soft iron core, that's why it's called soft iron core, and all the pole shoes, which are also soft iron, you want them to forget the magnetism as fast as it can. You want it easily magnetized, very high permeability, and low retentivity. That's why I tell you all that. All right, let's talk about ignition systems. Yes. The Kettering, Kettering, Kettering ignition. Well, one of the easiest ways to explain any type of ignition system is to start with a Kettering ignition system, also known as a battery ignition system, as a battery. Now, before we go too far, our aircraft that we work on do not have battery ignition systems. Why not?
Old school batteries die.
It's old school because batteries die. Not if you have an alternator.
Yeah, but if your alternator goes out.
Okay, what if the alternator goes out? What if the alternator goes out? Then what happens to the battery? Battery dies. Then what happens? Engine dies. And then that's not a good thing. So with a magneto, we have how many magnetos per engine? Two. So does it need a battery?
No.
Nope. How many are there?
Two.
What happens if one fails?
Hopefully the other one does.
Hopefully the other one does it.
Well,
Lon telling you about when both of his failed?
Yes, he has told me about that. And I've had experiences too in my shop where somebody has done something stupid and caused them to fail. So that's the unfortunate thing. Sometimes if one fails and the same person did them both, then they both will fail because of the same mistake. So that doesn't work. All right. So where are we going to find kettle ignition systems? Well, used on older cars, some aircraft, some antique aircraft. Usually something like a home built or something like that, not certified typically. I've never seen one on a certified. Recently made aircraft, nothing since the 30s. Let's see, principle of operation. Principle of operation. Now I gotta let you get caught up because I gotta move over.
Don't look at me.
I didn't. I looked at my water bottle. Now moving over. Are we good? Are we good? We good?
Just go.
All right, just doing it.
Like a band-aid, just rip it off quick.
All right, let me see. Let's draw one. Don't. I'm not going to force you to. All right, what do we have?
Battery ready.
Battery.
Good job, man. He asked Christian.
What did Christian yell?
He said, what is that? And he said it was a battery. I said, good job.
Well, yeah, what was your thing the other day you kept yelling? I don't know. It was,
Gone speed.
no, it was some part. I don't know.
Frequency. I don't know.
Frequency. Yeah, that was what it was. All right, we got a coil. Have an ignition switch. Ignition switch. What does this look like I'm building right here there?
Well, let me tell you.
How about a transformer? Brett, that's not. All right, we got to have a distributor. We'll make this a Volkswagen. So. All right, so it's only got. What is this right here?
Spark points.
Spark plug.
Oh, man.
All right, and I want to go from here to here, so. Lots of turns on this one. That's going to be my primary or secondary. All right, so we'll bring this down to ground. And I don't know, just to be fancy, we'll come over here. What's that right there? Capacitor and breaker points. And a cam. All right. So we have ignition switch, we have battery. We have the primary coil. Primary coil. We have the secondary. Secondary coil. Secondary coil. We have a capacitor, or what's it called here? Condenser. Condense. S-O-R or E-R? E-R? Condenser? I think it's. All right. Breaker points. And a little cam. This up here is the whole distributor system. Distributor. All right, so let's take a look at what happens. Now, this is a very important thing to remember. Is this currently on or off?
Oh.
It is currently off because the switch is open. Magnetos are the opposite. You will kill somebody if you don't get this correct. When a magneto is open, a magneto is on. So in this state, as I'm holding it right here, it is completely and totally on. Because do you see a switch anywhere?
No.
Nope, there is no switch. So that means if I turn it, I will shock somebody. It works.
Tim, put your finger in there.
It doesn't work very well. So I can't turn it fast
Well,
enough.
then you lied.
So, all right. So put your finger in there. I will work on turning it fast. Last thing I freaking do. So this is on. It is on. When it's in the aircraft and you think, oh, I should do something to make it safe, I will take off the ignition switch wire. What did you just do?
Make it on.
You turned it on. And then somebody touches the propeller, and you've seen how slow it can go with that impulse coupling, right? Barely turns, and that impulse coupling snaps. What do you get? Spark. If there's any fuel at all in the cylinder, what's that going to do? There it goes. You can take a propeller and move it this fast, and if there's fuel in there, it is going to start and go. And it's going to chase you down. And, oh, there's a really good movie I could show you guys about that one. Maybe I will. Not right now, but I'll have to find it. So I want you to remember that. A magneto without any wires is on. When the switch is open, it is on. It needs a ground to kill it. So a ground kills it. It shorts it out. So make sure you get that right. All right, so back to this. So this is right now off, right?
Right.
And we're going to turn it on. So now it is in the ON position. All right, so what's going to happen here is if these are closed, these are little points, contact point, little switch, all right? And so when the little breaker point switch is closed, making contact, I'm going to get current flow. We're going to use, okay, this is a good example of why it's easier to use conventional theory than electron. Because electron, I got to start here, and I got to find where I want to come up. But here, I can just draw through, because the line's already there. And I can say it goes through the switch. So it goes through the switch, and it goes through the what?
Primary color.
Okay, it goes through the Does any current flow through the core? Okay, this is the soft iron core right here. It's transformer. Any current flowing through there? No. All right, so all we have is current flowing through here. It comes around. What's it going to do with the condenser? It doesn't really. It's kind of it goes there, but it's going to see it more as an open because it's DC current, right?
Yeah.
So it's going to come through here, down, around, and back. So here you can see that I have a series circuit. Yes?
Yes.
I know you're like, oh God, back to that. So I got a series circuit. All right, that's all fine and wonderful. What's happening to this coil?
Creating a magnetic field.
It's creating a magnetic field. And we could use the left-hand rule of thumb, and we could do it. We could say, hey, current's flowing around a certain way, and I've got maybe north up here, or I got north, south here. Does it matter? Doesn't matter at all. But you have some sort of magnetic field is going to be generated, and that magnetic field is going to expand out in all directions. Goes to the left, doesn't do anything. Well, in reality, because my drawing is very two-dimensional, but in reality what happens is you have this primary wrapped around the center, around the core, and then the secondary on top of it.
Yes.
I can show you through the magic of bandsaws.
I'm not saying.
It's gonna cut off.
You can see this one?
So you're saying that the soft iron core is the south.
That's not What? You just make it converted?
I'm just trying to explain what the soft iron core is.
It's the hot dog and bun, dude.
All right, so here is one of
Pig in a blanket. It's
those,
just a pig in a blanket.
those coils cut away. So here's the secondary and here's the primary. Actually, I think this is half of the primary, or half of the secondary. It looks like there's all secondary split in half. But you can see that inside there, the primary has got a lot of turns of heavy wire, and then the secondary has got
Fine one.
fine wire. How many?
A lot more.
About 200 times?
200 times.
200, about. So we have the soft iron
Says
core.
about 20,000 times.
So that's what I just said. So, Tim, don't break that. Okay, so it's wrapped that way. So it's not like it's got to go right and it cuts across and left. It doesn't. These things are wrapped around each other. So when inside the soft nougat core there, we've got a
Yeah.
magnetic flux is going to build up from the primary and wrap itself entirely around the secondary. So what do we have? Let's say it, we've got an expanding and contract. Right now it's expanding. So we've got we turned on the switch on, it expanded out. What expanded out? Flux, and it cut across the secondary, and I have a step up or step down transformer. Step up transformer. Well, the thing about that is, you have to cut it, but you have to have relative movement, right? But if you have slow relative movement, it doesn't really do much. If I have a magnet and some wires, I just kind of go at those wires kind of slow. Or you want to grab my little light with the little tinker toy thing? So if I go slow, I've got nothing. It has to be rapid. It's got to be rapid. So, rapido. So this opens up. Well, okay, so I built up and it comes across here. But it was because this is closed. And it built up. And so what happens now is the point's open. So so this has to be timed correctly so that it opens at the right time. And that time in an aircraft engine happens to be about 25 degrees after top dead center. These points are going to open up. Oh yeah, so I have my little light. So does it do me any, I've got relative motion, I've got magnetic lines of flux, and I've got lots of turns. Do I have anything? Why not?
Of course, you need the speed.
I also have to have the speed, so it's gonna work. Okay. So you gotta have the speed, right? Because to not have speed gets me nothing, so gotta have speed. So I gotta have speed. So these breaker points open, and I have a sudden collapse of the field. Thank you, because that's where I want it. And bam! Sudden collapse of the field. I have rapid movement of the field dying off across the secondary. That's the same thing as spinning my little tinker toy fast. And I get a huge step up of 18 to 20,000 volts.
Yep.
It depends, really. We're going to see that in a second. It has the capability of it. So this all dies off because the point's open. Why is this condenser here?
So when you arc across the point, super condenser would be the easier path than jump across.
Okay. So if it wasn't for the condenser, what would happen is
You like the Titanic.
it would not be like the Titanic.
It would just be jumping off.
So what would happen as the points are opening, the current is going to, the voltage is high enough that it will cause current to continue to flow as they're opening. You're just going to see it arcing across as it opens, and that's really hard to time. It's going to be delaying it. So when you wanted this sudden and rapid collapse, especially at the right time, you're not going to get it. It's going to delay it as it continues to roll. And then eventually the points will be open far enough that the current will stop, and that is not at all what we want. We want it to happen right now when we said so. So to get rid of that, as I said before, the condenser pretty much tricks the electrons into flowing some other way. So the electrons want to go this way, but there's a guy over here, a little electron, says, "Hey everybody, I found a shortcut. That way's no good." So all of the electrons are going to go back. They don't really, but they come back and they start filling up here. Like, yes, shortcut. And then eventually they realize that they can't jump across. They're mad at this guy, because he's the one that said to come this way. Everybody go back the other way. So they all try to go back the other way. And by the time they get here, well, the bridge is too far to jump.
Way to screw that one up for us, Tim.
So,
Right.
yes, so it didn't work out. Well, it doesn't really work that way, but kind of. So back to the secondary. Meanwhile, we had this secondary, had a rapid and sudden collapse. We had a buildup of thousands of volts, and those thousands of volts are sent down this wire, and there's going to be a moving part in here that is going to be going around, timed off of the camshaft. And if it's aimed at this one, the electricity is going to flow here, jump a little gap to this, flow out of here, and jump across here and find its way back to ground, which comes back around over to here. So there is the complete path through it. Now, I tell you that, we said, okay, how many volts? 20,000. Doesn't have to be. Doesn't have to be. And it can be more. So it has the capability of, we'll say 20,000 volts. But if, for some reason, I want it black, just because. If for some reason there is no gap, it goes right to ground, it's not going to build up that much voltage right here. Does it need to? Whatever voltage is there, it's just going to cause the current to flow and go right to ground. But if I take this and I open it up and I make a very large gap with a pen, very large gap, we need a very large gap. If I make a very large gap, it's got a long way to jump. And in order to jump that, the voltage has to build up. So really the amount of voltage you're going to get out of the secondary is purely dependent on how big of a gap it has to jump. If it's got a very small gap, it's going to build up just a little bit because current can jump across that and flow. But if you have a very large gap, it's going to build up to its maximum, if it can, to jump that gap. So the further apart you go, the more voltage it is. And that's why in our magneto tester that we have, the gaps on those little pins, if you notice, all right, they have to be calibrated. And if you read the book, which most of you guys have, you will notice that I think it's 5, sometimes some are 5, some are 7 millimeter. Why it's millimeter, I don't know. But you have to set those gaps and adjust them. So your coming in speed is defined as what?
RPMs.
RPM that.
You get complete spark.
The lowest you can, or lowest you'll get on spark throughout.
Okay, so the coming in speed of a magneto is the lowest speed at which it will consistently fire all gaps. Now, you can't just say something like that, especially in aviation, because if I made the gaps 1 millimeter, I bet you could run that thing about 10, 15 RPM and it would work just fine. If I made them 6 inches, they ain't never going to work, right? So you have to have a calibrated point on there, and that point is based upon all that. What?
Is the distance of the points correlate to the complete burn of the fuel?
What?
Does the closeness of the points correlate in any way to the burning of the fuel?
Does the closeness of the
If
points?
they were further apart, would you have a more complete burn?
Oh, okay. You're talking about the points up here, the gaps.
Yeah.
If they were further apart, would you get no? Because really, once you start the burn, you get the burn.
Then why would you make them further apart? What would the point of that be?
Because so why would I make them further apart? Number one, you have, I've never read this, but you're gonna expose a certain amount. It's too small. It's only 18 thousandths of an inch. So if it's too close, you're gonna get a weak spark because you don't need a lot of voltage to jump the gap. So you want a gap that's far enough that you actually get a nice blue spark. Okay, so a perfect example of this that I could show you is right next to the tool room window for the second year class, there is a spark plug test bench. All right, so it allows you to clean spark plugs, and when you're all done cleaning, you screw them into this machine, put an electrode on and hit a button, and it puts AC current through there and just buzzes, and you just get this constant spark going across there. There's a little window, and you can look and you can see the spark. Now, if you just do that, screw it in, put the electrode in, push the button, the spark is going to be an orange color. And it's not very bright. It's kind of a dull orange. But on the machine, there's a little dial where you can put compressed air in there. And so you start putting the compressed air up, and that spark turns from this dull orange to this bright blue. So what's going on to change that color?
Fuel.
Well, it's a spark plug tester. I promise you we're not going to put fuel in there. That would be somewhat dangerous.
Something to burn.
Frequency.
Compressed air.
Heat.
Just tell us.
Okay, I'm gonna have to. I'm gonna have to. But I have to think of the answer while you're. I don't know yet. I'm thinking about it. Yeah. Okay, so inside of a cylinder, if you think about it, what are we doing to the air? Compressing it. Air is an insulator or a conductor. Air is an insulator. All right, so to the spark plug, if I'm at room temperature, we could just say to the spark plug, it appears as though the gap, and we'll just make up something, is like 7 millimeters at room temp, just standard atmospheric pressure. Thus the reason why you have a very large gap in the test stand. But if you start packing all of these molecules of air into that space of a spark plug, which is only 0.018 of an inch, when you pack all these molecules in, it starts to look to the electrical circuit like it's getting wider and wider and wider of a gap. It takes more and more voltage to jump it. So as I put the air pressure on this little machine, what I'm doing is I'm packing more air in between that little tiny gap, and it's in effect like taking the gap and spreading it out. And so it takes more voltage to jump that gap. And so what you're seeing is the yellow, the orangish spark. It's a very low voltage spark jumping the gap. Just very easily comes across. It's not a big deal. The blue is a higher voltage jumping the gap. So that's what's happening. You're seeing the voltage increase, and that's why the color changes. And you can see more molecules are smashed in there, so it takes more voltage to jump it. And that's why you actually put air on the spark plug when you're testing it, because you have to simulate what's happening in a cylinder. In a cylinder, does it have standard atmospheric pressure? It's got a lot of pressure, which makes it like a very wide gap. Is that a question? Stretching?
Yeah, I have a question.
Yeah.
If you have a bad spark plug, and I think that I was reading the Q&A that made the engine vibrate, right?
Okay, if you have a bad spark plug, we'll make it vibrate. It can a little. Remember, aircraft have dual ignition systems, so it can be a little bit tricky, because if you have one bad spark plug, you have 4-cylinder engine, you have 8 spark plugs, you still have that cylinder firing. However, there are some engines that have staggered timing. That's very critical. One spark plug goes 2 degrees before the other one, and that's to get the flame front, because of we'll talk about this later. The flame front, they want it to meet in the middle, and if you light it off from one end, it doesn't. So it's an uneven burn, and then you can get a little vibration from that. So, all right. So do you see how this is going to work? And the voltage that the secondary produces is purely dependent, not purely, but it's very, in large part, dependent upon the gap that it has to jump. So not only is it the physical size of the gap, so I could use, like in the lab, points that I spread out 5, 6, 7, 8 millimeters more, but also if I just take something like this that's inside of a cylinder, the more air pressure I put in there, so PSI, the more PSI I put in here, the more voltage it's going to take. And a refresher, what does PSI stand for? PSIG,
Gauge.
pounds per square inch gauge. PEPSI, that's just Pepsi. It's better if I don't write it, but
Can I ask you a question?
yes.
So you were talking about using the compressed air on the spark plug tester.
Yep.
Do you have to adjust the voltage accordingly?
Nope, you're just putting the voltage in, hit the button. Turn the air pressure up, and the voltage, you can tell that it just takes more voltage to jump it.
But what's telling it that it needs more voltage? I mean,
Well, okay, it's just, and I'm glad you asked that, because it's really the point I was trying to make here. There's nothing here telling it that it needs more voltage, is there?
no.
No. If the finger was, we'll just kind of make it like this. We'll get rid of this one, and we'll say the finger comes back over to here now, and we'll go to this one. But this one's got a problem in that it just goes right to ground. How much voltage is going to be generated in the secondary right to ground? Really not a lot at all. Why is a lot of voltage not created? Because as soon as current starts to flow, it just flows. Doesn't take much voltage buildup. All right, but then I come over to here and I want to go to this one here. How much voltage is going to be built up? A lot. Why? Because it's going to build up, build up, build, and there's nowhere for it to go. So this voltage just keeps building up until it's got somewhere to go, and the only place it has to go is to jump the gap. So finally, it's going to jump this gap. Back down here, it just goes, it just kind of meanders through. It's like, there's just a path. I don't have to build up. I don't have to do much of anything.
So when you use that compressed air, it acts like you were saying as a widens the gap.
Yep.
So it increases the voltage.
Yes, it doesn't physically do it, but how do I want to say
But
it?
It's more insulated.
Yeah, you're packing insulators in there, so it just appears that it's. Yes.
When you say it builds up there, do you mean like it's building up there in that?
Building up there. What do you mean? The voltage?
Yeah,
Kinda like
like
them.
Yeah.
will it send it over in the same time that it builds up as it's hitting that?
Speed of light,
that-
man. Speed of light.
Okay, so it's not like missing that cylinder.
Yeah, it's not like, well, this is going to take a minute.
Okay.
It's still happening around the speed of light. I'm sure that, you can measure it in something, but not with a stopwatch.
So you need the high voltage to pass this gap.
Yep. Yes.
If the secondary make a low voltage, it won't pass
Right.
this gap.
So let's just say we had a short somewhere, and so the secondary voltage, half of it's not working, and it's supposed to be able to give me 20,000 volts, but for some reason half of it's shorted out, so the best I can get is 10,000 volts, and that's not enough to jump the gap, then you got nothing. It's not going to work. Or things that might happen. It might work at idle because cylinder head pressures are low. And if cylinder head pressures are low, this system sees the spark gap as being very close. And all it takes is 10,000 volts to jump it. Put your foot on the gas, open up the throttle plate, and put more air into the cylinder. You have more pressure in the cylinder. Then it's like that gap starts getting bigger and bigger. And suddenly this system, it can't handle it. So you start getting cylinders are missing and banging and snorting and doing all kinds of crazy stuff. Back off and it idles fine. Give it the gas and pop, pop, snap. Nothing's working again.
So, comparing this to like the magneto
Uh-huh.
system, I know like on the magnetos you want to collapse the primary flux at its greatest current to get the maximum voltage.
Yep.
in secondary. Does that apply to this or no?
Okay, so I like that. It does apply to that, but this is far more simplistic in that where do we get the current for the primary? Battery.
And I know the mag is the
Oh, yeah, that's going to be more complex. So right now, current just flows to the battery. So when these breaker points close, this is going to build up to its maximum. How long does that take?
5 times.
5 times. How long is time constant? Well, I don't really know, but how in seconds how long that's going to be. But it's pretty dang fast. So this is going to build up pretty dang fast. And so it builds up. This opens up. Bam! Opens up. It dies off. All right. So that's just your basic Kettering system. It's really not much more complicated than that. But this is, again, one of those things where if you don't understand this, the magneto is going to be just magic to you. And you're like, well, I don't know. It's just magic and it's unknowable. So you have to look at this and go, okay, I understand all these concepts. I understand one, ignition switch. This is on. It's opposite in a magneto. Number 2, this is a transformer. The primary current comes from what? A battery. And it has an iron core, comes across the secondary. The amount of voltage produced is strictly dependent upon what sort of gap it has to jump, if it has to jump one at all. What the condenser is for and what the breaker points are for. Got it? All right. Did I say, are you ready, kids?
Sure did.
Are you ready, kids? Maybe that's how we should start our things every day. Are you ready, kids? And then you guys all say, aye, aye, Captain, and then we start. Okay, go. Did I write? I'm looking for my notes. I think I already wrote Kettering. I also put also known as a battery ignition.
Yes.
All right. So, I put B, used on older cars.
Yep.
Did I put C, principle of operation?
Yes.
Oh, right. So this is now just under I. So under principles of operation, battery supplies. Battery supplies, well, 12 volts to a primary coil. What is wrong with that statement?
So it only has one port.
Well, this also works for tractors. It works for older cars, so it could be 6 volts. It's whatever voltage. What's a bug? 12?
Yeah.
So don't get offensive, man. Don't.
Yeah, there's early model 6 volts.
Okay.
Yeah.
See? There are 6 volts. Oh, I have a Jeep that has 6 volts.
We have a Cessna out there that's 6 volt.
No, we do not.
Don't we? That German,
We don't.
oh,
Do you?
well.
The German Cessna? Das Cessna? What?
The 172 with the Mercedes, the diesel one.
12. It's 12
Oh,
volts.
that's right. Oh,
Yeah.
Was that? I thought that was 20 volts.
I know. That's how somebody exploded, literally exploded the innards of the.
That's what's up.
Yes, that's what's up. Now I know who did it. All right, battery supplies, whatever voltage. Like I said, I've got an old Jeep that has this system, and it's only got a 6-volt battery. So it provides whatever voltage it's designed for to the primary.
Well, we got a bunch lying around, Kevin, if you need a spare.
Hang on while I help Tim out. Got it?
I got it.
Okay.
He's beyond help.
All right, points, open and close. Open and close via a cam driven off of the camshaft. All right. And I forgot, I changed out 309, so this is going to be a problem now. Okay, so why is, number one, this distributor finger, this finger that goes around,
Which finger?
this one right here, that one goes, and it's tied to the cam. So really, these two things are usually physically right on top of each other. And they're driven off of a camshaft, not a crankshaft. The crankshaft is the thing that goes around, makes the pistons go up and down. All right, they have the three. Could you take care of him? Could you? I mean, ADT. Come on, he's supposed to take care
He
of
doesn't
him.
work for him anymore. He quit.
He's a
He
shot
did
caller.
quit.
He quit.
Was this because of us?
Yeah. He said, you guys give Kevin shit. I quit.
I'm just quitting until December and then I'll go back in May.
Okay.
Hey,
He's not even a good quitter.
Taking a break.
All right. So, talking about 309 people
Yes.
that didn't have engines this time because I cut it out. So in the engine, we have a 4-stroke engine, which means that the piston goes, there's 4 strokes. The piston starts at the top and it comes down. That's the intake stroke. Okay? It pulls in fuel and air. Then it goes back up and compresses the fuel and air, and on its way up, the spark plug ignites. And then the piston continues to go up, and then it comes back down. That's the power stroke. So we have intake, compression, power. The last one is exhaust. So on the intake stroke, we have an intake valve is open. And then on the compression stroke, it's closed. On the power stroke, they're closed. Then when it comes up on the exhaust stroke, the exhaust valve has to open up and let all that dirty, nasty air out. Comes up on the exhaust stroke, pushes out that dirty, nasty air. Intake valve on the other side opens and it comes back down. I have a video. Take me too long to find it. So, no, it won't. Let me think about that one. Are you guys leaving already?
You're goddamn right we are.
We'll watch the video.
All right.
No, we're just backing up, Kevin. Don't worry about it.
I know. All right, so this is just a 4-stroke engine. We'll slow it down. All right, so right here I've got the intake valve, my spark plug, my exhaust valve, and this is the camshaft here. This is the crankshaft. So crank is coming up, power, stroke,
Points opening up.
exhaust, intake, compression, power, exhaust. So this crankshaft is going to go around twice to make that happen. But the camshaft is going to only go around once to make that happen. And what you can't see is the camshaft actually goes in the middle, and it's got a little lobe that's also doing the same thing over here, but they only show it half. And this is a battery system, so we can actually kind of put it all together. I don't know if that, there we go, the cam is kind of working. So when those open up, that's going to fire. So the point I'm making is this goes around twice, this goes around once. So the camshaft is directly tied to what's going on with the valves and the spark plug. All right, so you guys are in a hurry to go, so I'll
Alright, see you, kiddo.